again. Morning, and thank you for joining us RC design class. I'm very happy to be here with you again. And quick announcement, I finished the homework number 4 updating, and 5 and 6 are following tonight. Uh, Not a whole lot you have to worry about in terms of grading, and there were some common mistakes made, but those are actually inherited mistake from the compressive reinforcement sections. That means few of you made a mistake of computing moment flexure strength, that is for the doubly reinforced sections. You may want to go back and check again how you do that. And sorry again, if you have a question, please unmute and say something, or else please stay away from mic so we'll have less disturbance. Okay, so that's about the homework. And for the exam, I have uploaded a video yesterday from the office hour where I talked about the type of exam and the type of problem actually we're going to be looking at tomorrow. I made a problem already. From the uploaded video, there were 4 problems from 2017. And this time around, I made only 3 problems, basically combining problem 1 and 2 from the previous exam in terms of types, okay? The problem will be totally different, so be prepared that you'll be answering quite different of, information there. One thing that I haven't mentioned clearly is about the section on the irregular section design. Okay, so for the irregular section design, we might have one problem to solve for the exams. Okay, I am making 2 sessions of exam right now, so one of it you might be see a irregular section. For Jared question, are you going to grade the remaining homeworks and quizzes before tomorrow? Yes, I just said that I have finished all the grading. I just haven't transfer all the graded portion to the internet where I used to print it out. Okay, so those will be updated tonight. All right, and like I said again about the exam, so there might be different versions. So one version you might see in the irregular section. If you're locked out, you might not see it in the irregular section. Okay. If you were to see in the irregular section, it will be pretty straightforward. It will be some section you've seen before. For example, if I can draw here, and hopefully you can see my screen, it would be something like this, like an opening duct like that, or something like this, and you have a little bit higher opening ducts, right? Now, the difference you probably are very aware of is that for the higher duct, right, the compressor zone might cover the duct. For the lower duct, you have to check whether the compressor zone is entirely covering the duct or not. Okay. Now, this is for the irregular section in the exam, right? You might see. Now, we have tested some other weird shape of irregular section before. For instance, we have tested something like this, which is an I-beam and with an opening here. And that looks a little bit too crazy. So I don't think we might make a T or might make a T section, but I don't think we're going to use an I-beam for the irregular section. Okay, so all I'm saying is you may want to dust up the homeworks that you did, or most importantly, the lecture notes you did on the irregular section, so you can prepare for the exam. Okay, so that's one thing I did not mention yesterday. Now, the other thing I did not mention is that for the shear problem, you may see a problem like this, right? Where you have an opening again, like the duct, but this is really an opening here, and you have stirrups going like this way, hopefully. Okay, for this scenario, you need to use BW to calculate your VC, right? Remember, VC 2 lambda square root F prime C, BWD, right? Now, D is no brainer, right? You can find easily by finding the location of, wait 1 second, by finding the location of the longitudinal reinforcement, right? You can find D, right? That is no brainer. It's BW the challenge, right? So I'm using the red color. This is BW, right? This plus this, okay? Or if you want to use the B opening, right? This is B, so BW equal to B minus B opening. Okay. All right. So it's going to be the narrowest width. So this is for a section that has openings, right? What if I have, sorry, let me use a different color. And what if I use a IB, right? So it looks like this. And you were asked to find shear, and then BW is right here. Okay, BW right here. So you notice that's always in the narrowest width along the section. Okay, so that is for shear. And last for the one-way slab, Jane, I have to mute you. Okay, sorry about that. For one-way slab, okay, usually, right, from yesterday's lecture, and I finished that in terms of calculation, the final number, you can take a look at it, right? But this is maybe too much, but anyway. So I have a lot of spans, right? So the only thing that you need to worry about is that take a look at the clear span, okay? This is the clear span, which is Ln, and this is adjacent span Ln1, Ln2. When you're trying to find the moment coefficient for the support, you gotta use the average. Okay? All right. So that is the most critical thing for one-way slab. And since we haven't said so many problems about one-way slab, we would not give any complicated problem on the one-way slab. It would be very straightforward, like the lecture notes, just a regular one-way slab. Okay. But you may have to do a design. All right. So if I were to do the design, just wanted you to see the whole picture. So this is the one-way slab that looks like, and then I have a strip, right? And be careful when you do the strip, because if you were to design the longitudinal reinforcement, and let me say this again, you're designing for slab, not a T-beam, okay? You're designing for slab, not a T-beam, okay? So slab goes this way, reinforcement-wise goes this way, okay? This portion is not slab, all right? Not slab. Just don't confuse yourself, all right? This portion is beam, support underneath it. Slab is going this way, all right? So for this, right, for the reinforcement in the slab, one thing you just have to be careful, be mindful, is that when you design for this slab, right, everything is per foot. Everything per foot, okay? Now, we will have a problem that you need to combine the knowledge on the moment coefficient, okay, coefficient of moment, and to design this. So how to design this, right? For example, if I have a coefficient of C here, say negative 1/16 omega u ln squared, okay, and this omega u would be the applied loading we talked about, right? In this case, omega u should equal to 1.2 dead plus 1.6 live, and we'll give you the live number, we'll give you the dead number, and the dead number you have to calculate, right? It is rho HF, and HF, you know it, it's the slab height. Okay, same thing here, slab height. Okay, now for this, C equal to minus 1/16 omega u ln squared. Ln is an average because it's at the support, okay? And then at particular location, right, this moment here, mu at C equal to minus 1/16 omega u ln squared, okay? Once you calculate out, it will be some number, but it will be kip, of course, foot per foot, kip foot per foot. All right, so I want you to pay attention to this unit here per foot. And with this, you can go to the lecture notes where we talk about how we design the reinforcement using this number, okay? Using this number. All right, and then if we were asked you to do the shrinkage and temperature reinforcement, you know, the shrinkage temperature reinforcement going the other way, and you see that this is not a T-beam, okay? Let me say it again, this is not a T-beam, all right? This is not a T-beam, okay? This is for slab, right? And notice the location, the reinforcement is within the slab portion, not in the beam, okay? And these are the temperature and shrinkage reinforcement. And if you forgot how we design for that, there are codes, requirement from the lecture notes. Simply go back and you'll find out. You'll find out, okay? All right, last thing but not least, when you design for both flexure, which means the longitudinal reinforcement, flexure, color is messed up, sorry, or you designing for the transverse, right? Either way, right? Either way, you have to make sure that you find the spacing. That is what you're designing for, spacing, okay? Spacing. So you know, per the ACI code, there's a conversion, right? How to convert the provided reinforcement to the reinforcement per foot. Remember that equation? Go back and dig it out and familiarize with that. Okay. All I'm saying is you can see already, right? So if I were to give you the design questions, right? Except the problem one be short answers, right? Problem two and three will be full calculate out problems, right? You are probably looking at irregular section, shear, and one-way slab. All right. So these are the details. Okay, I have one hands up. Sergio, any question for me? Yeah.
Yes.
Mm-hmm.
So whenever we work last class about the example of the one-way slab,
Yeah.
whenever we confirm the ACI moment coefficient,
Mm-hmm.
we use like just the span length between the columns. But whenever we, in step number 2, whenever we determine the coefficients, we use from like we use ln equal the distance from the center of the column to the center of the column.
I
So I was
see.
just a little bit confused about that.
Sure. Let me stop sharing this and go back to the previous lecture notes. I made a correction there, and if you haven't looked at it from the Canvas file folder, you should be able to see it. It should be always the clear span.
Okay, always a clear span. Perfect.
Right. Let
Yeah,
me
that
just
was just my only.
right. Let me just show you that. Yeah, I noticed that there was a typo during the calculation, but I think I correct that. So if you take a look at this previous, oh, sorry, this is the previous selection notes. Can you see it? So here, I believe is where your question is
Yeah.
at, right? So you notice that I have corrected it to be
Uh,
12, 14, 12.
okay, perfect.
Yeah, and this is
Yeah.
12,
Right.
12,
Perfect. Thank you very much.
14, 12. Yes. Okay, you're right. I mean, that's a good observation. Always use the clear span. Always use a clear span. Now, you may ask, okay, Bob, if it's always a clear span, why don't you give us? Well, in reality is that you're most time not given that. You just have to do a simple conversion. Okay, simple conversion. So I'll provide this number in the exam and provide the width of the support. You just have to do a conversion first to get this over with. Okay. All right.
Awesome.
Okay.
Thank you.
Yeah, no problem. Okay. Any other question about this? Okay, like I said, this one-way slab problem or example have been updated and uploaded to the Canvas. So please do take a look at it because you will need it for the exam, okay? You will need it for the exam. All right. Any other question for the exam regarding the time
What
and
was it? What was it uploaded under?
uh it's under the file folder.
No, I meant like what file?
It's lecture 17.
Okay.
Yeah,
And also with time, can those who have accommodations get their time accommodation?
like I said again, the exam was scheduled for 1 hour for all of us to finish. And 3 hours is extra time already for all of us, actually. And I don't think I have a problem with all the students finishing it. But if you have problem, you can email me. We can try to address that separately. Is that okay? All right, Emily. So I take it that is okay. You're muted, by the way.
Yes, it's okay.
Right. So I think the original exam is scheduled for 1 hour, and we let to be 3 hours because it's online format and trying to make everybody convenient. All right. Any other questions for me on the exam? Anything else? Okay. So if not, let me share my screen again. Let's come back to the class. Okay. All right. So quick reminder again, the exam is going to be tomorrow, 1 to 3, oh, sorry, 1 to 4 p.m. All right. Now, I will this time. I will set it up in such a way that you can upload to Canvas directly and without any hiccups. I hope this time. All right. So I will send the email again to remind you tomorrow morning during the exam, maybe when getting close to finishing up the exam. So you don't have to send me email. But if you feel uncomfortable, you can still send me email. Whichever timestamps comes earlier, that will be your submission time. All right. Okay, so let's get back to work. All right, so now here, today, we're going on lecture 18. We're going on lecture 18. Okay, now this is the new chapter we're going to talk about, and you'll see this in the final exams. Okay, this is the serviceability. Serviceability. Okay, so what is serviceability? Anyway, right? What is serviceability? Now let's take a look at the design spectrum. Design spectrum, meaning how did we design our structures based on what, essentially, isn't it? So you think about it, right? We have talked about first the strength design, isn't it? So let's say design for beam members, right? For beam members. That is predominantly for bending, right? And then for design of beam members, we said, okay, look, there are shear, there are moment, right? So let's take a look at the moment, right? So this is the moment. Under moment, we said, all right, look, we have done the singly reinforced, doubly reinforced, okay? And then we have applied that to both the known section and unknown section, okay? We have covered all that. This is for designing for moment, right? And for shear, right? So for shear, it's the same thing, right? But usually shear, we have known section, right? So this is for sterile spacing mainly. And this is a known section. Okay. Excuse me. And we also talk about one-way slab. Talk about one-way slab. And in the one-way slab, we also said there are flexure and there are temperature and shrinkage. Shrinkage and temperature. Right. So these three are the three types of detail or three types of design we have provided. And apart from that, last but not least, we also have to consider our bar detail. That means the spacing, right? How do we put the bars in the beam? That means minimum beam width, so on and so forth, concrete cover, so on and so forth. Okay. So if you really take a look at what we have learned, it's not much. This is what we have learned so far. Okay. And this is very systematic, right? Nothing special about it. However, though, you see that for all of them, we have been always using for strength criteria. And this we have covered in the very first lecture, chapter 3 design or chapter 2 design. Okay, that means everything was based on load carrying or load bearing capacity. Load bearing capacity. Right? In the sense is that we want to reinforce our section to have that the mu or the applied or factored moment and shear vu and has to be smaller or equal to phi mn or phi vn, right? So that was our process. That was our process. Normally, we were given this, and we just have to provide this, right? That was the design. So the whole thing so far is based on the strengths, based on the load carrying capacity strengths. Okay. But now today we're going to show that not only we have to care about the strengths, we also have to care about the serviceability, right? So let's recall design criterions. There are two design criterions, right? So one of them is strengths that we have done. Okay, and this is in terms Mn, nominal flexure strength, Vn, nominal shear strength, and we're going to cover later Pn, the column, right, compression, axial compression strength. But in parallel, we also have other things to consider. For example, the serviceability, right? Serviceability. So what does serviceability entail, right? Serviceability entails deflection, meaning the beam cannot bend too much, right? And cracking, meaning the section cannot crack severely. And bonding, excuse me, bonding means the concrete and steel has to work together, right? So among of the three today, we're going to focus on deflection. We're going to focus on deflection, right? So what is deflection? Deflection, say, take an example of a simply supported beam, right? Simply supported beam. If I have a concentrated force, of course, and the beam will deflect in such a manner that will gain a maximum deflection here in the middle span, delta, right? And if you remember from your structure analysis class or mechanics materials, this delta is usually a function of EI. E is the elastic modulus or Young's modulus, and I is the moment of inertia. That is to say, if we were given the E and I for a section, I can calculate my deflection, right? So the game is straightforward. We just have to satisfy the delta and let it to be smaller than the delta critical. And this is from ACI code, right? Then we're fine. Then we're fine. But in reality, it is not that easy or not that simple to calculate the deflection. All right. Sorry, I got questions. One-way slab design going to be tomorrow's test? Yes. Okay. Oh, answered already. Thank you. All right. Coming back to this. So the delta, which is the deflection, right? You need EI, but EI is not that simple. Why it's not that simple? You think about it, right? So when we talk about concrete beams, we often refer to a rectangular section, isn't it? And you're in your mechanics materials class, remember, if I have an elastic beam, when I have an elastic beam, my Young's modulus stay as a concrete Young's modulus. Is that right? But question number one, what about steel? Right? What about steel? You say, what about it, Bob? I mean, steel is steel, right? The problem is ES, right, is almost 8 times more than EC. The steel is stiffer than concrete. So how do we consider that, right? So whether should we consider that or not, right? That's question number one, right? So question number one, what about steel, right? How do we incorporate steel into the calculation of Young's modulus or moment of inertia, right? Question number two, what about crack, right? So what about it? If I have a beam like this, right, rectangular section, remember how we did the moment of inertia? Is that we assume the compressive zone is only at the top, right? And here concrete is intact. Matter of fact, we use F prime C, and if I want to be more specific, it's 0.85 F prime C. It's not even F prime C at failure, right? Meaning that the response is nonlinear. The stress response is nonlinear. And also, if you remember that we ignore this section because the tensile strength of the concrete is almost zero. It's almost zero. Okay, so that means a moment of inertia for this concrete section cracked, okay, is not the intact moment of inertia. They're different. They're different. So you cannot just do the 1/12 BH cubed to get the I, and that is not correct. That is not correct. So we have to figure out a way to do this. Okay, so this is something we're going to cover next for the serviceability. Essentially, it's just trying to find EI. Okay, so if I want to summarize these two problems, so let me do a summarizing. So this is simply just trying to find EI. okay, for different stages, okay. All right, so after all this long introduction, let's take a look at learning objective, what we're trying to learn, okay. So learning objectives, these are the problem that we're gonna make our exam, right, make our exam by. So one, we want us to determine the moment of the moment of inertia for uncracked transformed, okay, uncracked transformed section. So why transform? That means we have to consider the reinforcement, okay. So that answered the question number one, essentially, yes, okay. And we also have to determine moment initial for elastic cracked elastic transformed section. And this is to answer question number two. All right, this is the answer question number two. Okay, and of course, with that, we will be able to calculate the stresses of uncracked transformed section and also the cracked elastic section, the stresses. Okay, so these are something we need to know how to compute. And last but not least is that we need to be able to calculate, right? Calculate. So deflection, right? And also crack control provisions from ACI 318. Okay, so these are something we need to take care of. Okay, these are something we need to take care of. All right. So you may ask, what are these learning objectives? What do we need this for, right? These are the essence of the content that we're going to design our exam surrounding, right? Surrounding this, we're going to design our exam. So you just want to take a look at it. All right. Okay. So now to answer all these questions first, let's take a look, right? Recall. Let's take a look. Recall 3-stage of flexure behavior of RC beam. Reinforced concrete beams, that is. Okay, 3 stages, right? 3 stages. So if I want to describe a cracking of a beam, right? So think of it. At beginning, if I have a beam, I bend it. All right, I bend it. So when I bend it at the beginning, everything's elastic. Everything's elastic. All right, that means uncracked. Okay, so let me remove this. Sorry about that. Uncracked elastic. Uncracked elastic. Okay, what does really mean? It means that straight plane remains straight, right? All these small strain diagrams are linear. So the strain diagram looks like this. So strain diagram looks like this. And the stress diagram looks like this. Very linear-like. Okay, so this is called uncracked elastic stage. So everything's linear up to this point. Okay, so let me call it number one, uncracked elastic. So if I keep increasing the bending moment, right? If I keep increasing the bending moment, what happens? What happens is that if I draw the beam again, shorter, I start to see hair crack, right? At the bottom of it. Start to see crack at the bottom of it. Okay, and these are fine, right? Because concrete was not designed to take care of the tension anyway, right? We always have reinforcement in it. we always have reinforcement in it, right? So as my bending moment keep increasing, I just start to see crack within the section. So everything else stays elastic. Everything else stays elastic. That means if I draw a hairline where underneath the line are cracked region, up there are the compressive region which are not cracked. So the whole thing is still elastic. Okay, so I call this stage of cracked but elastic. Okay, cracked elastic. Now the stress distribution in this stage, again, whenever you see the word elastic, there's some region has to be linear. All right, there's some region has to be linear. That is to say, look, if I have a section, right, and I want to draw it, and now the bottom part loses already. No concrete anymore connected. The compression zone is here at the top. The compressive zone is here at the top, right? So if I want to draw the stress distribution, right, and this is the stress distribution. Compressive stress in the compression zone, and this is linear, okay? This is linear line. At the bottom here, I just have my rebar reinforcement, so I have tension going out, okay? Tension going out like that. So that is the cracked elastic stage. Okay, cracked elastic stage. Now, as you progress along, keep increasing my moment, right? So if I keep increasing my moment, let me try this. This is delta M, and keep increasing more, right? What will happen? What will happen is that my horrible drawing here. Let me just correct that real quick. What will happen is that now the crack here are severe. You see a lot of cracks already, right? On top of it, the reinforcement at the bottom here yielded already, reaching the yield point. Okay, so here at this stage, this is failure or yielding. So we call it ultimate strength, meaning the section has reached ultimate strength. And in terms of stress distribution for this, you already know, right? I have a concrete that is almost nonlinear, and we use the Whitney stress block, but before that, the actual stress distribution looks like this, remember? Was hyperbolic like, and then the tensile reinforcement reaches Fy. And here is F prime C. Okay, so that is ultimate strength. All right, so here, let me just add this one, M plus delta M. Okay, increase the moment. All right, so if I were to draw the response in the plot, now when I draw it, let me just make the y-axis to be the moment. Okay, and let me make the x-axis to be curvature. Okay, you may already forget about this. What is curvature, right? Curvature simply is the rotation angle here, phi here. Okay, all right, so it's describing how much bending we're seeing for the beam, right? So following the three stages, beginning is linear, okay? Beginning is linear, right? So now let me go this way here, straight line from the origin, straight line from origin. And I'll hit the crack load, MCR, where first cracking occurs, okay? And you see that I will enter a very short plateau stage, meaning no increment in terms of moment to a lot of increment in terms of curvature. All right. And after this point now, I will enter the nonlinear zone. Nonlinear zone. Okay, nonlinear zone. All right. And then finally, I will reach the plateau, which is the ultimate strength zone. Ultimate strength zone. Of course, when I reach the yielding strength, right? And this is my Mn. This is my Mn, the moment capacity. All right. Now, if I were to label the stages, right? So you see that this is stage one, uncracked, elastic. Okay. Stage one, right? So let me just label this like that. Okay, and this is stage 2, cracked elastic. And this is stage 3, ultimate strength. Okay, so that's how we label the 3 stages on this curvature, moment versus curvature curve, moment versus curvature curve. Okay, now why do we care about this? Because today, or in this lecture, the deflection we'll need a calculation for is describing from here to here, right? So this is where we need a deflection calculation, so-called survey stage. Okay. Now beyond this, in stage 3, the beam fracture cracked already, right? Enter the final stage, so we don't really have to worry about it. Okay. So deflection means serviceability is just concerning number 2 and stage number 1. Stage number 2, stage number 1. All right. Okay, so that is the concept, how we deal with deflection, Okay, like I said in previous section, it's all coming down to how do we determine the Young's modulus and moment of inertia for the section, right? So you start to think about it, for the uncracked section, it's not that bad, right? Stage 1 is not that bad. So stage 1 is uncracked, elastic, right? Uncracked. And for moment inertia, all I have to do is take a look at the section, right? This is the section, right? And I just want to calculate the EI. But I have a problem. What kind of problem? Not only I just have a concrete, if I just have a concrete, I can just straightforward calculate my EI. I have steel here, reinforcement here. Okay, and we know that this is not going to happen because we need transformation. Because since RC beam is a composite beam. In your mechanics materials class, you should have learned that this is composite. 2 materials mixed together, right? Composite. And because it is composites, EC, which is modulus concrete, roughly equal to 57,000 square root F prime C, right? And steel is, this is concrete, and steel is about ES 29,000 KSI, and this is PSI. All right. So if we were to compare them, let's define a factor and ratio is called N, and this is called modular ratio, and equal to ES divided by EC, steel over concrete. And give you some number for F prime C equal to a 3 KSI regular concrete. This ratio equal to 9.3, very high number. Okay. And for F prime C equal to 6 KSI, this number drops to 6.6. All right. So these are quite high numbers. What does it mean? It means that if I have one number 9 bar, for instance, if I have one number 9 bar steel, that equals to, in this case, 9.3 inch squared of concrete. And that is quite significant. So in this case, you cannot design or treat RC design monolithically. Meaning you cannot treat as one materials at all monolithically. Okay, so what to do, right? This is the question. What to do is we need to convert steel to concrete. And one more thing, when we do that, we do the conversion, set N approximately equal to n period. Sorry, approximately equal to 8 period. Okay, don't have to worry about the strength so much. We're just going to use average n approximately equal to 8. Okay, so let me show you an example. Let me show you one example. Okay, so I have a section, say this. Okay, rectangular, nice looking section. And I have a bars at the bottom here, 3 bars. The depth of the section looks like this. Okay, and the width of the section, call it B. I have a height of the section H. Okay, and I would say that let's assume I have reinforcement, total reinforcement of AS. All right. So how do I transform? How do I transform? Okay. So assume AS 3 number 9 bars, 3 number 9 bars. Okay, and ES equal to 29,000 KSI. Right. What I want to do is what is my I transformed? Okay, so this is example number 1. Okay, so to do this, right, first of all, let's do a quick calculation. What about n modulus ratio? All right, so in this case, n equal to ES over EC, right? And let's not plug in the number yet, just set it like that. Okay, and then I look at this, right? I look at the section. Let me redraw it. Look at the section, right? So concrete is here, the bulk, and I have reinforcement here at the bottom. Here, 3 number 9, right? I want to do what? I want to do 2 steps. First of all, I'm going to erase this. So what I do is I will just take them out. Take them out. Okay. And once I take them out, I will put another slender bar like so to replace that. Okay. And now this will be the transformed concrete. Sorry, let me respell this. Transformed concrete. Okay, simplify by doing what? By doing this. So ATR, let me call this ATR transformed concrete area would equal to N multiplied by AS. AS. So the idea is I can transform my steel into a bar like this and then compute the moment inertia. Then proceed to calculate moment inertia. And the reason I can do that is pay attention, right? So I can set this to be almost like a 1 inch. This is arbitrary, okay? A width of a strip, all right? And I can place them in the same level of the original steel reinforcement. Why do I need that? And I'll show you next lecture why. But in a nutshell, it is I want to get the right distance from the steel to the center, to the neutral axis. Okay, so this ds prime stays constant. Okay, and let me not use that. Sorry about that. Let's use y bar or ys. Stays constant. Okay, so the 2 steps involve first transform the steel into this slender strip of concrete, then perform the moment inertia, which we'll talk about next lecture, which is Monday next week. All right. Okay. Now we won't have homework this week since we're having an exam. So I'm gonna stop right here and ready for any question regarding to this or the exam tomorrow. Okay. All right. Let me stop recording.